In this video tutorial, we're going to be introducing polytropic processes, and in particular, we're going to be looking at polytropic compression and polytropic expansion. We're also going to introduce pressure volume diagrams, or PV diagrams, and see how these can be used in order to determine pressures and volumes throughout a given cycle. So in this particular tutorial, we're going to be evaluating the refrigerant R410A. And we're going to go through a cycle. Now each of the steps in the cycle are outlined in the bottom left hand corner. The first step in the cycle is going to be adiabatic compression, and we'll talk about what we mean by adiabatic compression in a moment. We're then going to have isobaric expansion, followed by polytropic expansion, and finally we're going to have isochoric cooling. Just to explain some of these terms then, what we mean by adiabatic is a compression or expansion process where no heat is gained or lost to the surroundings. It's best described as a constant heat process. Next we have isobaric, and isobaric means constant pressure. So during any isobaric process, the pressure at the start and the end of that process must be the same. Next we have a polytropic expansion, and unlike with adiabatic processes, polytropic processes do either lose heat to the surroundings or gain heat from the surroundings. And we're going to introduce something called the polytropic index, which actually determines how much heat is gained or lost to the surroundings. Now finally, we have an isochoric process. An isochoric means constant volume. So as we discuss each of these processes and determine our unknown pressures, volumes and temperatures, we're going to plot these processes on our PV diagram. We have a number of different equations that we can use for polytropic processes, and these can be found on the equations and information sheet for this topic, so I recommend that you print that sheet off and have it to hand, so as we introduce each of these equations you can see where they actually come from. So first of all then, we have an adiabatic compression. Now before we can evaluate an adiabatic compression, we need to know the adiabatic polytropic index for our R410A gas. Now the adiabatic polytropic index can be calculated by doing Cp divided by Cv. So the adiabatic polytropic index is dependent on other constants for the particular gas. I've given the values for Cv and Cp for the refrigerant R410A. Cv is 735 and Cp is 848.9. So carrying out a quick calculation, we can find our adiabatic polytropic index to be 1.155. So now we have some information we can work with, because we know as we go from position 1 to position 2, we have an adiabatic compression. Now when we compress a gas, its volume decreases and its pressure increases. So on our PV diagram, we can represent that as follows, going from position 1 to position 2. Now stated in the bottom left hand corner, we've said that that's an adiabatic compression and we're compressing the refrigerant to 0.6 litres. Therefore, at position 2, V2, we know we have a volume of 0.6 litres. But what we don't know is the pressure at that position, and we also don't know the temperature at that position. So those are the two things we need to find next, using our formulas for polytropic processes. Note that the formulas for polytropic processes still apply, but instead of N, we're going to use the value of gamma of 1.155 for our adiabatic process. Okay, so if we want to find the pressure at position 2, we can use the following formula. P2 over P1 equals V1 over V2, all raised to the power N. Now because this is an adiabatic compression, N can be replaced with gamma. So we can rearrange this formula, and instead we have P2 equals P1 times V1 over V2 to the power gamma. Now providing we're consistent, we can input both of our volumes in litres, because converting both of those volumes from litres to metres cubed would give us the same answer for this bracket. All we have is a ratio of the two volumes. And once again, we can use our pressure P1 in bar providing we remember that that's going to give a value of P2 in bar. So we just need to be consistent with our units and make sure they correspond. So inputting some values, we have P2, the thing we're trying to find, equals P1, 4 bar, the ratio of V1 to V2, and we're going to use litres. So we've got 2 over 0.6, all raised to the power of gamma, 1.155. Now running that through the calculator gives a value of P2 in bar, remember it's in bar here, P2 equals 16.07 bar. Next we're going to calculate T2, and the formula for calculating T2 comes from the following. T2 over T1 equals V1 over V2 to the power of n minus 1. Now once again it's an adiabatic process, so instead of n we're going to use gamma. Therefore T2 equals T1 times the ratio of V1 over V2 to the power of gamma minus 1. Inputting some values, we get T2 equals T1. Now here we do need to be careful. These formulas are only going to work if we work in Kelvin. Now we've specified that we have a temperature 0 degrees C which we need to convert to Kelvin. Now note, to get from degrees C to Kelvin we need to add 273.15. So our value of T1, 0 degrees C, is the same as 273.15 Kelvin. So we have T2 equals 273.15, V1 over V2, so again 2 over 0.6, gamma minus 1, well gamma is 1.155, 1.155 minus 1 is just 0.155, giving us a value of T2 equal to 329.19. And remember, that's in Kelvin. If we wanted that temperature in degrees C, all we would need to do is subtract the 273.15 to get back to degrees Celsius. So I'm going to transfer the values for P2 and T2 to our diagram, and then we're going to evaluate the second process moving from 2 to 3. Okay, so as we move from 2 to 3, we have an isobaric expansion. Now when something expands, its volume increases, but if it's an isobaric process, then its pressure is going to remain the same. So on our PV diagram, we have a pressure that remains unchanged. Well, if the pressure remains unchanged, we must be moving in this direction on our diagram, like so. And the reason for that is because we have a constant pressure over here on our y-axis. And we're expanding until we get to 0.8 litres. Bearing in mind we're currently at 0.6 litres, the volume's not increasing by a huge amount, from 0.6 to 0.8 litres. So let's represent this as best we can on our diagram. So we're going from 2 to 3, horizontally, like so. And in the bottom left-hand corner, we've specified that the isobaric expansion takes place to a volume of 0.8 litres. So we know that this expansion takes place until V3 equals 0.8 litres. So V3 equals 0.8 litres, but what we don't know is P3 or T3. Those are the two variables that we're going to find. So as we've specified that moving from position 2 to position 3 is an isobaric process, we therefore know that P3 must be the same as P2, 16.07 bar. Now the other thing that we can do here is start with our ideal gas equation that states that P1 V1 over T1 equals P2 V2 over T2. Now by specifying that this is an isobaric process, P1 equals P2, therefore we can just remove each of those from the ideal gas equation, and we're left with V1 over T1 equals V2 over T2. Now I'm going to make one more slight adaptation to that because we're moving from position 2 to position 3, not position 1 to position 2. So instead, I'm going to write that as V2 over T2 equals V3 over T3. It makes no difference. We're just moving from the start of the process to the end of the process. Now we're trying to find T3. So the next thing I'm going to do is recip each side of that equation. So instead, I'm going to have T2 over V2 equals T3 over V3. And then the final step is to multiply each side by V3 to get T3 on its own. So I have T3 equals T2 over V2, all multiplied by V3. Now once again, we need to remember to work in Kelvin. So we have T3, which we're going to find in Kelvin, equals T2 in Kelvin, 329.19, divided by V2 and then multiplied by V3. Now for the reasons mentioned before, providing we're consistent and we use litres for both V2 and V3, we don't need to convert them to metres cubed. If we converted them to metres cubed, we'd get exactly the same answer. So V2 then is 0.6 and V3 we've specified is 0.8. Therefore T3 in Kelvin equals 438.92. Kelvin. Now it is worth mentioning that when we have an isobaric process, that's the same as a polytropic process with a polytropic index of 0. Therefore, you could have used the previous polytropic process equation and inputted the value of n equal to 0, and it would have yielded exactly the same answer for temperature as we've just calculated there. If you're unsure, then you can try that for yourself using the polytropic index of 0 and the equation T2 over T1 equals V1 over V2 to the power of n minus 1. Okay, so let's transfer our value for T3 to our diagram, 438.92, and then we'll evaluate our next position, position 4. Okay, so there's a couple of things to think about here. Going from position 3 to 4, we have a polytropic expansion, but we haven't been given the polytropic index. We're told that it's a polytropic expansion up to 2 litres. And then our final process, 4 to 1, is isochoric, and isochoric means constant volume. So I'm going to sketch position 4 on this diagram, and then we can look at how we know the location of position 4. So polytropic expansion, when a gas expands, its volume increases and its pressure decreases. So we're going to have another curve like so. Now what we know from the question is that the volume at position 4, V4, and I'm going to write it in the top right hand corner, is 2 litres. We have an expansion up to 2 litres. Now note that that volume of 2 litres is exactly the same as the volume V1, 2 litres. Therefore, we know that position 4 and position 1 must exist on the same vertical line. They have the same volume indexed on our x-axis. Now this is also backed up by what we know about the process 4 to 1. 4 to 1 is isochoric, or constant volume cooling. So as we can see, we have position 4, and moving from position 4 to position 1, we must have a vertical line. We have a constant volume process. Now the other piece of information that I'm going to give you about position 4 is the pressure, and we're going to say that the pressure at position 4 is known to be 5.8 bar. Now, there's a number of different ways we could have approached this question. Had we known the polytropic index, N, we could have calculated the pressure and temperature, but instead we've been given the pressure as 5.8 bar, and we're going to calculate the polytropic index, N. And once we've calculated the polytropic index, N, we're then going to calculate the temperature at position 4. And then we'll have a complete picture of what's happening in this process. So because we know the volume and pressure at position 4, and we know the volume and pressure at position 3, we can use the polytropic formula that we saw previously. We can use P4 over P3 equals V3 over V4 to the power of n. The only difference between the formula that I've written there and the formula on your equations and information sheet is that I've replaced P2 and V2 with P4 and V4, and I've replaced P1 and V1 with P3 and V3. All we're doing is we're looking at the start and end of that process and relating it to the cycle that we have described on the screen. So as we look at this formula, we know P4 is 5.8 bar and we know P3 is 16.07 bar. We know that V3 is 0.8 litres and we know V4 is 2 litres, but we don't know N. Now hopefully you recall from earlier tutorials, if we're trying to find the power, or the power is an unknown in our formula, then we need to use log laws. So the first thing that we need to do here is take logs of each side. Now in doing so, we'll end up with the following: log P4 over P3 equals log V3 over V4 multiplied by N. By taking the log of each side there, we're drawing the power down. If you're unsure what I've done there, then please refer back to our tutorial on the use of log laws. So on the right hand side there, we have log of V3 over V4 being multiplied by N. So in actual fact here, what I can do is divide each side by log of V3 over V4, and that's just going to leave N on its own on the right hand side. So I'm going to rewrite this slightly, and instead I'm going to write N equals log P4 over P3, which was originally our left-hand side, divided by log V3 over V4. Now I'm going to use both my pressures in bar because P4 over P3 is just a ratio, and I'm going to use both of my volumes in litres because V3 over V4 is just a ratio. And I get the following: N equals log P4 5.8 over P3 16.07 over log V3 0.8 over V4 2 litres, and that gives us a polytropic index equal to 1.112. That index doesn't carry any units. So what you'll notice is that our polytropic index here, 1.112, is less than the adiabatic polytropic index of 1.155. What that tells us is that heat's either being lost or gained from the surroundings. So we don't have the ideal reversible process, we actually have a polytropic process where energy is being lost or gained as heat. So I'm going to transfer that value of N, and then we're going to calculate the final temperature, T4. Okay, so now we have our polytropic index N. We can go on and calculate T4 using T4 over T3 equals V3 over V4 all to the power of N minus 1. Finally then T4, T3, V3 over V4 to the N minus 1. And plugging in some values, we have T4 equals T3, 438.92, times V3 over V4, 0.8 over 2 to the N minus 1. Well, N is 1.112. 1.112 minus 1 is 0.112, giving us a value of T4 equal to 396.11 Kelvin. So I'm just going to transfer that final temperature T4 into the top right hand corner, and then I'm going to show you how we can check that this is actually a complete cycle and that position 4 directly relates to position 1. So although we've already evaluated the pressures, volumes and temperatures at position 1, 2, 3 and 4, the next part we're going to do is quite nice as a check. It's not necessary, but it's nice to check that position 4 relates to position 1. Now if we start with our ideal gas equation, we know that P1 V1 over T1 equals P2 V2 over T2. Now, going from position 4 to 1, what we have is isochoric cooling, or constant volume cooling. So what we can actually do, if the volumes remain constant, is remove V1 and V2. Also, because we're working between position 4 and position 1, what we're actually saying is that P4 over T4 equals P1 over T1, so that we're relating that to our diagram. And we can just do a quick check. P4 is 5.8, T4 is 396.11, P1 is 4 bar, T1 is 273.15. So if we've accurately worked out each of our pressures and temperatures, then these two calculations should yield the same result. So on our left-hand side, 5.8 divided by 396.11 equals 0.0146. The units here are somewhat arbitrary. It would actually be bar per Kelvin, but we're just doing this as a simple check. On the right-hand side, then we have 4 divided by 273.15, and 4 divided by 273.15 equals 0.0146. So what we've shown there is that if process 4 to 1 is isochoric, then the ratios of our pressures and temperatures going from position 4 to position 1 actually prove that we have a complete cycle which starts at position 1, goes to position 2, 3 and 4 before returning back to position 1. In the next video, we're going to continue with this example. So we're going to keep the pressures, volumes and temperatures that we've calculated here, and we're going to calculate the work done on the gas or the work done by the gas as we move through each stage in this cycle.